Today I'll be talking about the strange case of privacy in equilibrium models, or why you shouldn't go around adding privacy to stuff. And this is joint work with Katrina Liggett, Malesh Pai, and Aaron Roth. So here we're trying to capture this thing that happens in practice where you see ads based upon your past purchase behavior. And here we have a single product for sale and two possible ads. And your value for this ad, your value for this product is correlated with the ad that is the best fit for you. And so probably if you're reading smart investing magazines, then you should be having like a Ritz-Carlton credit card. And if you're not very credit worthy, then we should show you this very sketchy looking credit card offer. And again, here we have one ad that is objectively better than the other. So to make things a little more precise, this is a 3-player game between a seller, a consumer, and an advertiser. And the seller has a single good for sale, and they're going to post a price P. And the consumer is going to arrive, and she knows her value for the good and her type that the advertiser cares about. And given all of this, she's going to make some purchase choice. Here she decides to buy at this price. And then the seller is going to send a noisy signal to the advertiser about her behavior. So he's going to flip a coin, and here, oops, her buy became a not buy, and so now she's shown the bad ad. And I'm going to talk about the privacy policy of this game, which here means what's the probability that we flip this bit Q? That we flip this bit, we're going to flip it with probability 1 minus Q. And we'll talk about how equilibrium of this game changes as we vary this privacy policy or as we change Q. And I hope to convince you that it's not at all obvious how this changes. So to make things even more precise, in the first period, we're going to have a consumer interacting with a seller. She'll have a value V drawn from some distribution F. We require F to have a monotone hazard rate, and that's all that we need. And there's a purchase price posted, and then the consumer makes a purchase choice, and B is her bit, whereas 1 if she bought, and it's 0 if she didn't. And then we're going to flip this bit, and we're going to call the noisy bit B hat, which is correct with probability Q or flipped with probability 1 minus Q. And in period 2, the same consumer is going to interact with an advertiser who has seen this noisy bit B hat. And there's 2 types that a consumer can have. And we'll think of T1 as being the better type, or that high type. So in the past example, being credit worthy is the good type. And the probability that you are the high type is some function of your value in the first period. And so this function G is going to be monotone increasing. So if you have a higher value for the good, then you're more likely to be the high type. And there's 2 ads that we can show, and we're going to have the first ad A be the ad that's just better. So here, a consumer gets a delta bonus for seeing the good ad over the bad ad. But the advertiser, on the other hand, wants to match people according to their type. So here he wants to show the high type, the the better ad, and the low type, the worst ad. And in case this is a lot, here's basically a cheat sheet of all this. We're going to send a, yeah, sorry, go ahead.
So here, once seller makes a decision, so the buyer makes a decision, so she's actually buying.
Yes, yeah.
And seller has to tell the advertiser whether she bought or not.
In a noisy way, yes. Yeah. Yeah, so this bit B is what actually happened. But this bit B hat is going to be a noisy random variable that's now correlated with her purchase choice, but isn't exactly correct. And that's what the advertiser is going to see.
And what's the incentive for seller to deliver?
For now, we're just thinking of this as being some like exogenously chosen privacy law. And we'll sort of see, in fact, how all the players' utilities change as we do change Q. So in fact, they will have an incentive to set certain Qs over others in equilibrium. Yeah. So we're thinking of this as the seller sending it, or possibly a third party. And we're sort of asking this question from the perspective of, like, if you want to make privacy policy, how should you set the privacy level? And as we'll see, like you sort of want some interior privacy level, and it also depends on who you're trying to help here, because these different players in equilibrium benefit from different privacy levels.
The utility of advertiser here is, you say, okay, like it wants to allocate the suitable ad, but what is the utility? You need to capture the quantity of the utility at some point, and there's a number of ads that you allocate properly.
Yeah, so you can think of this as a single shot game, or equivalently as like the same game happening with a continuum of consumers all drawn from the same F. And the sellers, wait, you're asking about the advertiser or the seller? Yes, yeah. So if I show a high type player the better ad, then I get this payoff as an advertiser. Yeah.
Here the buyer has an incentive to pretend to be, have higher valuations than reality?
Absolutely, yeah.
I've actually thought as a buyer, and I've actually tried to do the opposite I always want to make sure that the advertisers think they have, will your results somehow strongly depend on this direction?
Yes, yeah, they will. I won't say anything about it today, about why it matters in this direction, but it in fact very much does matter that having basically a high value today means that you get a better payoff tomorrow. And so part of where all these sort of strange things arise is because players in the first period are gonna buy at a price above their value. And so they're gonna take a loss in the first period to see the better ad tomorrow in certain settings. Yeah. And that we'll all see soon. Okay, so just as a cheat sheet of what's happening here, the seller is going to send a noisy bit that is correct with probability Q. T1 is the high type, and the ad A is the better ad. And if you have a higher value, then you're more likely to be a high type, and so then the advertiser is more likely to want to show you the better ad. Okay. So here, because this is a pretty simple game, for a fixed Q, we can just solve equilibrium using backwards induction. And we're going to need the following lemma that says in the first period, there's always a cutoff strategy of the consumers, where there's some marginal value V star, and if you have a value above that, then you buy, and a value below that, then you don't buy. So in period 2, the advertiser sees this noisy bit B hat, and knowing the entire game, knows Q and knows V star computes a posterior on the types. And this is some possibly complicated function that we're not going to write down today. And so the advertiser can compute his expected utility for showing each ad based upon his posterior beliefs about the type of the consumer. And he'll show ad A whenever this is higher than this, given the bit that he saw. And so you can just rearrange this, and he'll show ad A if his posterior belief about the consumer being a high type, given the bit that you saw, is above this thing, which for now we'll just call eta. And again, this is some possibly complicated thing. So there are three possible things that can happen, and they can be grouped into two different categories. There's a uniform equilibrium, where we're always going to see the same ad regardless of the noisy bit that was shown. And this can be because the advertiser's posterior is going to be above eta always. In this case, you're going to see the better ad, or because it's always below eta, and then you're always going to see the worse ad. And it can also be a discriminating equilibrium, where if your bit is 1, then you see the good ad, and if your bit is 0, then you see the bad ad. And we also have a lemma in the paper showing that the posterior given 1 is always higher than the posterior given 0, and so these are the only three cases that can happen. So in the uniform case, things are really simple. Oh no, what have I done? Okay. So in a uniform equilibrium, what you do today doesn't affect your payoff tomorrow, because you're always going to see the same ad regardless of your purchase choice and if your bet is flipped, and so you might as well just behave myopically. And so you're going to want to buy at a price below your value, and the seller is going to want to charge the monopoly price. And again, because players are being myopic, then the price is exactly this V star cutoff. And so we can rephrase this up here and say that a uniform equilibrium exists exactly when the advertiser's posterior, given that the monopoly price was charged and consumers behaved myopically, satisfy these conditions up here. But if we're in a discriminating equilibrium, then consumers are going to want to be strategic in the way Aviad mentioned. And they're going to want to think, if I buy today, how is this going to affect my payoff tomorrow? And so they're going to be forward-looking, and they're going to consider their future payoff as well. And so they're going to buy whenever their value now, whenever they're surplus from buying the good, plus the probability that they see the better ad tomorrow times the delta bonus, is better than what they would get if they don't buy, which is basically 0 today, plus the probability that their bit gets flipped into a 1 times their bonus. And so you can rearrange terms, and this has to hold with equality for the marginal buyer, and so you get this expression. And so note now, this Q appears here in the location of the marginal buyer. And again, the seller posts a price to maximize revenue. It's not the monopoly price anymore, because we have this sort of more complicated thing happening. And again, we can phrase this in a more formal way, which is that a discriminating equilibrium exists exactly when the advertiser's posterior, given the V star that solves this, satisfies these conditions above. So this has all been for a fixed Q. And so now let's think about what happens as we change Q. Well, as we increase Q, we're saying that the signal we send is more accurate, and so there's sort of less privacy happening here. And so again, here in a discriminating equilibrium, the location of the marginal buyer is going to move. So this cutoff V star decreases, but the signal is more correct. And so in some sense, we're sending a more accurate signal, but just has different content. And we can't really say, without looking deeper, if this is better or worse, is it more informative or less, because it's really going to depend on the distributions of the values and on the types given values. And we can also view this change as basically consumers are buying themselves more privacy. And they're changing their action to sort of protect their true information, but this comes at a cost, because often means that these players over here are going to buy at a price above their value. And so they're sort of taking this costly step to buy themselves more privacy. So for the rest of the talk, I'm just going to show you some pictures of what happens if you plug in a few specific, if you plug in a specific distribution and parameters. And I'm just going to show some plots that show some of these surprising things. So this here shows plots as a function of Q. We have the mutual information between the advertiser's posterior given the noisy signal and his prior on types. And so basically what I want you to see is that it's non-monotone. So in fact, if you are at some Q region over here and you think, well, this is too much privacy, so I'm going to send a more accurate signal, well, you can actually be decreasing information as you increase accuracy. And so this is sort of, I think, the main surprising thing that can happen. And we view this almost like a Laffer curve for privacy. And for those of you who don't know, yeah, chuckle's good. The Laffer curve is a thing from macroeconomics where you plot the tax revenue as a function of the tax rate. And if your tax rate is 0, then you obviously make 0 tax dollars. And if your tax rate is 100%, then you don't have an incentive to work, and so no one works, and so you have zero tax dollars. And there's some like place in between where you make positive tax dollars. And so here, this is sort of like the same thing happening for privacy, where at the extremes you basically don't get like anything good, but there's some sort of sweet spot in the middle. And this depends really on your game parameters, exactly where this sweet spot is. But it's important to know that it's not monotone. Yeah.
So Q is the probability that you flip, right?
Q is the probability that's correct.
Q is the probability that what you said is correct.
Is
so
correct,
one
yeah.
Q is the probability you flip, right?
Yes, yeah.
And so if you flip this probability one, and that's the y-axis
Is the mutual information between the posterior and the prior. So here we're sort of going from complete privacy over here to no privacy over here.
No, this was the y-axis.
Oh, the y-axis is a mutual information between the advertiser's posterior and prior, which is a measure of basically how much information is contained in the signal that we send. Yeah. How much time do I have left? Okay. Then let me skip some other things and show you some more plots without telling you how they came from. But so these are sort of plots of the utilities for all players with two different parameter values of eta, and some things that you should immediately see are that they're non-monotone and they're not continuous, and there are discrete jumps, and there are places where for example here we don't have any equilibrium existing, and so we just don't have any values here. They're non-monotone, And this is basically the same game, and you just change one parameter value, and this is the advertiser's parameter eta that sort of captures which ad he's going to show. And so if you have the exact same game and you change one single parameter, then, for example, the blue is the consumer's surplus. So if you increase Q from being half to something bigger, you can either have a big jump in the consumer's surplus or a big drop, depending on your game parameters. And again, these jumps come from basically changing in between a uniform equilibrium and a discriminating equilibrium. So the main takeaways that I want you to get from this is basically if you just add privacy to games without thinking about the incentives of the players themselves, then you can very often have the exact opposite of the intended effect. And this is sort of in contrast to the differential privacy literature, which assumes that you have some fixed database and you can just choose the privacy level to optimize your sort of privacy accuracy trade-off. What's critically different here is that when you choose a privacy policy, the data hasn't been created yet. And so the data itself is actually a function of the privacy policy that you choose. And so if you want to decide privacy levels in strategic settings, you should really think about what kind of game is happening here, what are the incentives of players, and also who are you trying to help. Because as we saw on the last slide, different players have different optimal privacy levels that they prefer, and so you should decide before you begin, am I trying to help the seller or the advertiser or the consumer, because that should affect your choice of a privacy level. Thanks. Yeah, Rita.
So coming back to my
Mhm.
question, so what if the person who is actually providing the privacy somehow is also a player, like is also incentivized? Is there any work helping do that?
Yeah, so at least in this setting as it is right now, it's sort of not clear like what the incentives of that person would be. If they're one of these three players, then we can say what they would choose to set the privacy level. If there's some like fourth player, sort of like they might have some incentives, but it's not clear what that would be explicitly in this game. One thing that we don't capture, but I would like to do in the future, is some notion of having the seller also price a signal to the advertiser and sort of having this be a part of the game of not just pricing the good, but also pricing the signal and having the advertiser choose at some price which noise level they want to see. Unfortunately, in the model as it is right now, we're sort of not able to say that because we take all the advertisers for parameters and we just smush them together into this function eta. And so it's sort of like, basically there's no way to naturally restrict them to be on the same terms as like everything else. I mean, say if the function has support 0, 1, like it's not clear sort of why the advertiser's utility should also be in 0, 1. If you do restrict that, then you can look at it, but sort of it doesn't fit naturally into our model, although I wish it did.
Also, like seller may want its own advertisement to be shown, so that could be another.
Yeah, definitely. And I hope that there are ways to extend this model to sort of capture like the more robust world in which things happen online.
Any other